All right. Good morning.
Morning.
So what we'll do today is to finish up the double precision floating point number representation. We'll get a second lab, which I think it would be pretty easy to do given the first lab is done already, but I cannot give you the solution of the first lab yet because that's going to give you that kind of defeats the whole purpose because the second lab is kind of like the first lab except it's the reverse of what we do in the first lab. So I'll talk about the second lab a little bit today. Basically just the logic of it. Um, and just like last time, we're going to switch to 16-bit, for the integer size, just so that we know how to do it. But other than that, we may have about 15 minutes, maybe 20 minutes worth of material left with double precision floating point number. And then we're going to switch over to a new topic that will lead to actual assembly language programming, which is the title of this course. So that's going to be what we'll be doing today. So there'll be an important transition today to the newer topics. All right, so let me move this out of the way because it's actually in the recorded session portion. And I don't think I need to do any handwriting today, so there's no tablet handwriting setup today because I think everything that I need to do I can use a spreadsheet. Um, we'll see. It won't take me too long to set up the tablet. It's maybe about 15 seconds or so. All right. The YouTube site is streaming already. I just confirmed that. Um, and obviously in Discord, I'm live streaming as well. So it's time to get started. So let's go ahead and get started today. So today's remaining topic for double precision floating point number is what if the exponent of 10 is more than 0? Then what are we going to do with it? So it depends on how much it is more than 0. If it's just a little bit more than 0, it's no big deal because we can always multiply the mantissa by 10. So every time we multiply the mantissa by 10, we can decrease the exponent of 10 by 1 because we want to preserve the value being represented. But beyond a certain point, that's not going to work. So let me kind of show you what I mean by beyond a certain point is not going to work. So what we'll do is I'm switching to a spreadsheet, okay? Because a spreadsheet allows me to kind of illustrate how the algorithm applies, and also I can do a lot of math stuff in a spreadsheet. So what we'll do is we're dealing with 16-bit unsigned integers for the mantissa, which also means the mantissa can only represent values from 0 up to 65,535, which is not a whole lot. And also the value that we want to represent in this case, let's make it kind of really big, okay, like 1.23 times 10 to the power of 60. Okay, so we know that this cannot fit into a 16-bit unsigned integer because a 16-bit unsigned integer can only handle up to about 5 digits in base 10. And we know v itself is going to have, 61 digits in base 10, so it's not going to fit. So now the question is, what are we going to do? Well, at least initially, what are we going to do? And then when it cannot fit anymore, what are we going to do at that point? So the initial phase is pretty easy because how we represent v is we have the mantissa, which is 123, because we remember we only use unsigned integers to represent the mantissa. And the exponent of 10 initially is not 60 because we shift the decimal point 2 places to the right hand side, which means we have to decrease the exponent of 10 by 2. So this is what we start off with. And then exp2 has an initial value of also, which is 0 in this case. All right, so that's what we're going to do initially, okay, the easy part of it, okay. So the easy part of this, okay, if I were to use a table to represent this, let's say this column A is representing the mantissa. Let's see. Let's put it over here, okay. So this is the mantissa, and this is EXP10, and this part here is EXP2. So we start off with 123 in the mantissa and 58 in exponent of 10. So the first part is really easy. We just say, well, let's keep multiplying the mantissa by 10 and by, oops, okay, let me do it one more time. So we multiply by 10, and as a result, we have to decrement the exponent of 10 by 1, sorry. So, and we can do this for a little bit, okay? We can do it, one more time, and that's it, okay? Because I cannot multiply 12,300 by 10 anymore, because if I did that, it would exceed what we can represent in base 16. So this is when we have to say, uh-oh, we have to stop now, because we can no longer multiply the mantissa by 10 and then decrement the exponent of 10 by 1, because the objective now is to decrement the exponent of 10 until it gets to 0. So we know we cannot do that anymore. So we look at this and go like, what can we do so that we can multiply the mantissa by 10 again? So we go like, maybe we can make use of base 2, right? So what we can do is now we say, let's look at this number divided by 2. Okay, we got this number here, but remember, every time you divide the mantissa by 2, you have to increment the exponent of 2 because we want to represent the same value the whole time. So this would still be 56 at this point because we are kind of stuck. We cannot do it anymore. So when you look at this value, you go like, this looks like a value that can use another multiplication by 10. How do we know? Because this value at this point is less than 65,535 divided by 10. So there's room for another multiplication by 10 by now. Now, what if you're dealing with a 64-bit integer? Well, you just have to find out what is the largest value you can represent using a 64-bit unsigned integer divided by 10. And if the mantissa is less than that amount, that means there's room for another multiplication by 10. Okay, so I just said it without actually writing it because it is also in the notes. Okay, so I'm expecting people to actually read the notes, watch the video, think about it, absorb the information and also the reasoning, understand why this works before they move on to do their homework or the lab. All right, so now that there's room, okay, so we say let's multiply the mantissa by 10, and by doing so I also have to remember to decrement the exponent of 10 by 1, but I'm preserving the exponent of 2 in this case. So at this point, the algorithm says, are we done? No, we are not even close to done because the exponent of 10 is 55 right now. The other thing that I did not do, but it would not make any difference in this case, is when I divide it by 2, I'm supposed to do some rounding here, right? So the rounding is done by taking the floor of D4, which is the current value of mantissa, plus 1 first before we divide it by 2. This is also discussed in the notes. This is how we do rounding without actually needing to use floating point number calculation. And that's one of the restrictions of both labs is you are not allowed to use floating point number calculations. So no log, no power, no double, no float. Okay, those are the restrictions of the lab because that kind of defeats the whole purpose if you're going to use log or something like that. All right, so it doesn't make any difference in this case, simply because these numbers will remain divisible by 2 for a while. So now we look at this number. We look at 61,500. And we go like, we cannot multiply this by 10 anymore because if I did, it would exceed the value range of a 16-bit unsigned integer. So what we'll do is we'll divide it by 2. Okay, so we look at this value And remember last time, when we divided by 2, we should do a floor, this value plus 1, the whole thing divided by 2, and finish the floor. So now we have to remember to increment the power of 2 by 1, but we are preserving the power of 10, or the exponent of 10. So we look at this mantissa and go like, do we have room for another multiplication by 10? The answer is no, because if I did that, we would end up with 300,000 something, when we can only represent up to 65,000 something. So nope, we're not done yet. So if we're not done yet, then we go like, let's divide it again by 2, and let's increment the exponent of 2 by 1 again. We look at this value and go, is there room for another multiplication by 10? The answer is no. So we have to divide it by 2 again, and then we have to increment the exponent of 2 by 1 again. And we look at this value and say, can we multiply this by 10, and would that fit in a 16-bit integer? The answer is still no, because we would end up with 76,000 something when we can only represent up to 65,000 something. So we have to divide it by 2 again and increment the exponent of 2 again. And all this time, the exponent of 10 stays the same. It is 55 the entire time. So now we look at this particular value as the mantissa, and finally we realize that it is less than 65,535 plus 1, the whole thing divided by 2, minus 1, excuse me. It's less than 65,535 minus 1, the whole thing divided by 2. So we now go like, maybe we can multiply this by 10 again. So we do that. Okay, we take this, we multiply by 10, and there's no rounding to do when you're multiplying, because it does not introduce an error. There's no need for rounding. But when we multiply the mantissa by 10, we have to remember to decrement the exponent of 10 by 1, but we are preserving the exponent of 2. So now we go like, okay, this is great. We just got rid of another exponent of 10. So now we look at this value, we know we cannot multiply this by 10 anymore. So now we have to go through the same logic to divide it by 10. So we look at this, we divide it by 2. And when you divide the mantissa, you have to do the rounding. So we have to add 1 to the 11, the whole thing divided by 2, and then take the floor of it, because we are doing integer division, which has a built-in floor function applied. We preserve the exponent of 10, and then we increment the power of 2, because the mantissa got divided by 2, so the exponent of 2 needs to increment. So you can kind of see how this is going to go, right? I'll finish another iteration, and I'll call it good, because I think from the spreadsheet, you probably know what logic we need to use. Okay, so we'll go ahead and do it a few more times. So we look at 19,220, and we know there's not enough room for another multiplication by 10, so we're going to have to divide it by 2 again. So once again, we take the floor of this value plus 1, the whole thing divided by 2. Keep the exponent of 10 and increment the power the exponent of 2. Looks like we need another division by 2. Okay, so we continue this particular approach, maintain this, increment that, and now we finally have room for another multiplication by 10. So we take this value, we multiply by 10, we decrement the exponent of 10, so it's 53, and we maintain the power of exponent of 2 like that. All right. So over the weekend, I got someone asking me, how do I check the value is right or not? Okay. Well, that Q is actually in the lab itself, okay, because what we want to preserve is the mantissa times 10 to the power of this number times 2 to the power of this number, which initially are zeros to begin with. Okay, so we want to look at V and want to make sure that V is preserved as much as we can. So we look at this and we say it is the mantissa times 10 to the power of this value. Oops. Time 10 to the power of this. There we go. Times 2 to the power of this. Okay. So we got our 1.23E60 back, and we should get the same value for every single row. And if we don't, that means I have made a mistake. Now this one here is because of a rounding error, and you can see with only 16 bits for the mantissa, we get enough rounding error for it to show up in 5 significant digits, but with 64 bits it won't show up for a long time. Okay, and that's also why we want to use 64 bits for the mantissa, because when you divide a 64-bit number by 10, the error introduced is so small that it is not going to affect the conversion process too much. There are some values in base 10 that can never be represented in base 2 and vice versa, but no, not vice versa, but because everything in base 2 can be represented by a base 10 number without recurring digits. But the idea is the more digits you allocate to the mantissa, the less error you will end up with during the conversion process. So the value being represented is going to be preserved a lot better when we allocate more bits for the mantissa. This is kind of extreme because we are only using 16 bits for mantissa, which is not a whole lot. All right, so I'm going to take a pause here and see if people have any questions about this example here while I go in and check out some direct message. So if you have any questions, you'll go ahead and type it in today's text channel. Okay, so there was a direct message that says, now I tell people about the restrictions. No, the restrictions was actually talked about in the first day when I first introduced the lab. I already mentioned it, at least verbally. So this is not the first time that I mentioned about the restrictions. No, I may not have written it in the lab, but I did talk about it in class. And remember, it was pretty specific too, that I said do not use floating point numbers. All right, so I got secure typing. All right, so, oh, okay. Oh, okay. All right, so that's good. All right. So this is what we have here. And we are pretty much done with double precision floating point numbers at this point. I also want to mention, I know I might be beating a dead horse here, but when you look at all the math, involved in section 5.2 and also section 5.2.1 and section 5.2.2, none of this requires floating point number calculation. Not even this, because by the very nature of integer division, the floor is automatically applied. So nothing here actually involves double precision floating point numbers. All right. So are we ready to transition to a fairly new topic? All right. I'm not getting any here. Okay, so the power function is also not needed. I'm getting a direct message asking about to use the power function. The power function is not strictly needed because you can use shifting, and the shifting operation is actually exact when it comes to integer arithmetics, as opposed to the power function, which is not exact. Which means if you subtract using the power function, if you calculate 2 to the power of 64 minus 1, and then you subtract that amount from the unsigned integer value, which is all 64, all 64 bits of ones, there'll be a difference. The power function is actually imprecise when it comes to the exact value for for integer values up to 2 to the power 64 minus 1. And that is also partially why we do not use double precision floating point numbers, is because of that. All right, so Sakil asks, just out of curiosity, does von Neumann architecture use even more advanced math than we have done so far? The answer is no. The von Neumann architecture by itself is more of a design philosophy, more so than some kind of math. So let's go ahead. I think when we get into what von Neumann architecture is about, we'll understand what it is, and by itself, there's no math behind it. But when we need to look at memory devices, then we have to get back to logic gates, because we have to understand how the computer can maintain memory when all it has are valves, right? Because the p-type transistors and the n-type transistors are really just two different types of valves, and the most basic difference between those two is how do we turn on the valve to allow flow, and how do we turn off a valve to shut off the flow. And one turns on when there's a presence of the quantity that we use for the devices, and the other one turns on when there's an absence of the quantity that we are switching. So we'll get to all that stuff. All right, so I'm going to close this module because we don't need it anymore. And I'm going to scroll down to von Neumann architecture and memory. And before we get into D flip-flop and other basic memory devices, I'm just going to talk about, overall speaking, what is von Neumann architecture, who is John von Neumann, and why the von Neumann architecture is such a breakthrough in the history of computer science. So there's a little bit of history, involved in this discussion, because I do want people to understand the significance of the von Neumann architecture. All right, so we are going to go take a look at some Wikipedia pages. This is really long. I'm not even going to go through the entire ENIAC Wikipedia page. It is very fun read for some people. If you like to understand the history of computer science and understand all the major landmark discoveries and inventions, the ENIAC is one particular landmark, because it is quote unquote a programmable computer to perform calculations mostly, and has all the concepts that we already know, right? It has got loops, it has got branches, it has got subroutines and stuff like that. However, there's a big difference between ENIAC and any computer that we encounter today. Even if you look all the way back, let me kind of figure out the time frame here. If you go back to the 70s, okay, 1970s, which is about 40 to 50 years ago, okay. When you look at those computers, they are already von Neumann architecture computers. So even though they're really slow, each processor only has one core and it only runs at 1 megahertz, okay, it is still as modern as our computer today in terms of the one particular aspect of the computer architecture. So the ENIAC is different from that perspective. So what we want to do is to look at the programming of this particular computer. So I'm going to look for the word programming. So the programming of this computer is, okay, I'll just highlight the sentence here because there we go. All right, so the highlighted sentence here talks about how this computer is programmed, okay? And it has nothing to do with how we understand about programming, or very little, okay? It's programmed by a combination of plug board wiring and 3 portable function tables containing 1210 way switches each. Okay, so now the question is, what exactly is a plugboard? Is that a programming language? The answer is no. A plugboard is not a programming language. It is a physical device. So if I take a close look at a plugboard, that's what a plugboard is. Okay, if you have taken some electronic classes and you have worked with breadboards, a breadboard is a modern day reusable low-cost plugboard, basically. And these plug boards are much more flexible. You can see how the wires just basically fly everywhere. And you can also, if you magnify, okay, come on, if you magnify enough, you can see how each wire terminates with a plug. So that plug just plugs into a receptacle on the board, and by wiring, using individual wires, you can now change the connectivity between the receptacles on the switchboard itself. That is how an ENIAC computer is programmed. Okay, if you want to change a loop, okay, if you want to change the logic of something from a loop into a conditional statement, you have to rewire it. Okay, and then the 10-way switch, the 1200 10-way switch each, for the portable function table, that just provides you with a gigantic plug board too. So how these individual switches, how each 10-way switch connects to another 10-way switch is done by wires. Okay, so that means if you want to change the program, there's a lot of physical work to do. And also it is not symbolic at all. You do not type your program. Some of you may have relatives, okay, who are still alive, who used to program computers using punch cards. Punch cards, by comparison, is like light years ahead of the ENIAC computer in terms of how they are programmed, because the ENIAC, you just cannot be programmed using the traditional way. You don't just write a program, compile it, and expect it to run. You have to go and change the actual physical wiring of those computers. That is prior to von Neumann architecture. Okay, so if John von Neumann did not invent the von Neumann architecture and no one else did, we would still be stuck in the stone ages of computing. Okay, there won't be cell phones, there won't be portable computers of any kind, because computers would be pretty big and gigantic in order to have switches or plug boards or wiring that we can disconnect and reconnect. So that gives you a little bit background of pre von Neumann architecture. So the next thing I want to talk about, which is kind of outside the scope of this class a little bit, but I think it's actually pretty interesting too, is to take a look at von Neumann. Okay, this is a last name. So John von Neumann is the person who came up with the idea of the von Neumann architecture, which we'll talk about in just a little bit today. So when you look up, the Wikipedia page on John von Neumann, it's really long. Okay, just look at the thumbnail here. Okay, it just goes on and on and on. So, and you also notice that I did not say, okay, when John von Neumann, this computer scientist, invented this architecture, blah blah blah. But that's because he's not just a computer scientist. If you look at his major contribution, the fields that he contributed to, he's not a particular expert in one particular field. He is good at a lot of different fields. And if you ask these people from the different fields what they think of John von Neumann, they will all say that he is one of the best in that field. So he is that good. Okay, he is good at many different branches of science and engineering and math fields, and he excels in every single one of those. So that's really kind of interesting. Unfortunately, he passed away really early. You can see that he passed away when he was only 53. And he died from cancer. And apparently his cancer may be partially because his involvement in the creation of the hydrogen bombs. So he was involved in the creation of the hydrogen bombs, and he was in the field as well. So I think most people think that he got radiation exposure because of that, and that's partially explained why he passed away so early. John von Neumann also taught at Princeton University, where a lot of famous scientists taught over there as well. And if I remember correctly, his time, John von Neumann, actually shared his tenure at Princeton University with Albert Einstein. So they actually share, the same hallway because I think they were both teaching physics at the time. And there were some really kind of interesting stories between those two because Albert Einstein is a very introverted person, and apparently John von Neumann is not. He likes to listen to loud polka music, which no doubt has to do with his Hungarian heritage, which Einstein did not appreciate. So kind of interesting stuff, for between big names in science and engineering. All right, so enough about the background stuff. Okay, so what exactly is the von Neumann architecture? So even before the von Neumann architecture, even in the ENIAC computer, there is memory implemented by I think the ENIAC still used vacuum tubes. So there are memory devices implemented by vacuum tubes. But the memory devices were only used to store the data to be processed. So John von Neumann's idea, may seem very simple from our perspective because we are so used to that idea. But at the time, it was a breakthrough. So John von Neumann's idea was, why don't we store what the computer is supposed to do as bit patterns within the memory of the computer? In other words, in addition to using memory to store the data that is being processed, all the partial results being calculated and whatnot, why don't we use that memory to also store what the computer is supposed to do? So instead of using hard wires, instead of using switch plug boards and whatnot to specify the behavior of a computer, let's also use memory devices inside the computer to also remember what the computer is supposed to do. That was his breakthrough. I understand by our standard, it's like, oh, you call that a breakthrough, but it seems just kind of logical because um, since the day when before we were born, okay, myself included, that's how computers were already. Okay, even from the late 50s and the early 60s, computers were using von Neumann's architecture already. So to us, it sounds 100% natural, but at the time, it was a breakthrough. So what we'll do now is we're switching gear in order to talk about how a computer can quote unquote remember something. How does a computer maintain the state of memory? Okay, so that's basically what this particular module is about. And I got some notifications when you guys put in comments into the share document. So some of you are way ahead and already into the D flip-flop and memory devices discussions, and that's great. Okay, I really like you guys to read ahead of me because that will help you understand the concepts a whole lot better. All right, so the first thing we'll do is we are going to take a look at an SR latch. Okay, so I describe an SR latch using text here. So if you look at this quote unquote code here, it looks a little bit like C++, right? If you look at NAND2 as a class, input pin as a class, if you look at output pin as a class, this is kind of like a program, okay? And circuit, which is a variable that already exists at this point, has a method called add node. And a node is basically a electrical connection between ports of pins. Excuse me, my phone is ringing. I'm gonna turn it off. So a node is basically just an electrical connection between ports of devices in Logisim. So we'll go ahead and create this particular circuit using Logisim and see what it looks like. So let me start up Logisim. go. And I want to maintain a view on the circuit, so I'll be working on the actual circuit in Logisim on the side here. So we'll need these components. We need 2 output pins, 2 input pins, and 1 NAND 2 gates. So let's go ahead and grab the 2 input pins, okay? And we'll grab the 2 output pins, like so. And we'll also need 2 NAND gates. So we can see these are NAND gates, and we already know that each NAND gate can be made using 2 p-type transistors and 2 n-type transistors. But instead of making my own NAND gate, because the point here is to illustrate the device that we're making at this point, there's no need to go through the trouble to create our own NAND gate. So I'm just going to use the one already in the library. So here's one, here's another one, and they are named in the code here. So one is N1 and one is N2. So I'm doing this just to show you, from the text description, there's an equivalent Logisim representation. The 2 input pins, one is called S, okay, and I'll tell you guys why it's labeled S and the other one is labeled R. And then the output pins, one is Q and the other one is NQ, which is actually just not Q. So one is Q and the other one is NQ, like so. So now, how do we make connections between these components? Well, those are all done by nodes, okay? So once we're done with the connections, I'll show you what a node is like visually. So the first node, which has no name, it connects the port from S, which is an input pin, to the first input pin or the first input port of N1. Okay, so we connect it from here to here. That is one node. The second one goes from R to the second input pin of N2. So that's another node. But when you look at the next 2 nodes, they have 3 connection points. So the third one connects the output of N1 to the input of N2, but also to the port of Q, which is an output pin. So we connect it to Q first, and then we also connect to the first input of N2, like so. And then the last one is from N2 to the port of NQ, but just like with the other one, it also connects to the input, the second input of N1. Alright, so now we have the circuit drawn, and let me show you what a node is. If you switch to the poking tool, every time you poke a wire, that represents a node. Every time you poke a wire, it is representing a node. Every time you poke a wire, it is representing a node. Just like that. So there are 4 distinct nodes within this particular circuit. But now I hope most of you can see how a node in this kind of representation of a circuit really just corresponds to the same common electrical connection that is simultaneously connected to various ports of various components. So do we have any questions about the equivalency between the text representation and the graphical representation in Logisim? Okay, no questions? Well, I have a question. Why are we suddenly switching to a text representation instead of a graphical representation? Well, graphical representation, excuse me, is intuitive. Okay, there's no doubt about the intuitive nature of graphical representation, but graphical representation also has certain limitations. Let me ask, how many people know what is MIT Scratch? Does anyone know what is MIT Scratch? Without looking it up right now. All right, nobody knows what it is. Okay, so I'll show you that what it is. So you just have to look it up. MIT Scratch, as in Scratch. Oh, okay, Catherine knows about it. So Scratch is interesting because it is a programming language that is graphical based. Okay, so let me see if I can just show this picture. Not just kids, I actually enjoy programming in Scratch a lot too, because you can make like very simple scrolling games and whatnot really easily using Scratch. It has a really good support for multimedia as well. So let's go ahead and just look at this image, and I'm going to zoom in, and you can see how the logic, they're all done by blocks. Okay, so Sakio has some experience using it too. Excellent. So it's a great little programming language, so to speak. There's no need to learn any syntax, because if two blocks do not plug, that means they're not supposed to connect, which would otherwise be known as a syntax error in actual text type programming. But in graphical programming, if it snaps, it's good. If it doesn't snap, no, maybe they were not meant to be connected. So that's really kind of the cool aspect of MIT Scratch. But if you try to use MIT Scratch to write a big program, okay, not even like gigantic big, just like your homework assignments for CISP 400 or 430, you will very quickly realize that, oh, this is a chore. Okay, I would much rather switch back to C++ or Java and not use Scratch for that purpose. So can anyone kind of guess why that is the case? Why Scratch is not suitable for specifying something that is relatively complex? And we are talking about CISP 400 or 430 level type of complexity. Yep, it gets messy. Okay, now if you have never programmed anything using Scratch, you would probably not appreciate what Sakio just said. Okay, it's messy. Because it's not line based, so you can just put your function and definitions everywhere. Wait, does it even have class stuff? That I do not know. I know it has subroutines, and over time, it evolved, to have more features. It may not have classes. You're correct. It may not have the concept of a class, but it has some really strange, interesting stuff for. Oh, it does. Oh, it does more than just loops. It has got multi-threading, and I think it can intercept keyboards and other events too, and that's why you can write games using it. But the point is, graphical programming is very messy. Okay, if you want to insert something into the middle of something, not that it cannot be done, but it takes a lot of work. Okay, but if you use a text editor, you just press the enter key, get a new line, and then you can insert code. So that is why in Logisim, even though it is intuitive, we can visually see how things are connected. It is sometimes not the best way to specify the logic of something that is complex. Okay, such as a processor. Okay, we have seen the processor, the very simple processor that I use for this class. But imagine a real processor. If a toy processor looks like that already, a real processor is going to look very messy when it is in a graphical representation. So that is the reason why I am introducing the text representation of logic circuits. Okay, I don't know how many of you plan to transfer to UC Berkeley, and at UC Berkeley, if you are pursuing the Bachelor of Science in Computer Science, because they have 2 degrees in computer science. One is a Bachelor of Art, and the other one is a Bachelor of Science. So if you're going after the Bachelor of Science for computer science, which I think they call electrical and computer science, or ECS, electrical engineering and computer science, EECS. That's it. They call it EECS. The final year project is to produce a fairly complex processor that has some features that my processor completely lacks. Okay, so that is not going to be in Logic Sim. Okay, there's no way you can specify a, well, I shouldn't say no way, but it is very impractical to specify something that complex using a graphical representation. So with that project, you'll be using one of the two popular what we call HDLs. HDL stands for Hardware Description Language. One is called Verilog, 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 and the other one is called VHDL, okay, which is, I cannot remember what the V stands for, but HDL once again stands for Hardware Description Language. It could be virtual, I cannot remember what it was. I probably can look it up really easily too. But the point is, okay, when your design gets complex, people would start to use text representation. Also, because in the text representation like this, you can utilize concepts like subroutines, okay? You can use loops, you can use all kinds of other things, so that it would be actually not too complex to write out, for instance, K64 for the carry look ahead mechanism, because you'll be just be specifying that complex logic using a loop in a loop, okay, and possibly using subroutines to specify how components are created and how components are connected. Okay, so that's really just a long introduction to why we are now starting to sometimes look at circuits from a text representation. So now that we have this circuit done, okay, the first thing you notice about this circuit is it is not very complex, okay? It only has two NAND 2 gates, okay? So by comparison to, let's say, the circuitry of K2, or even K1, okay, this is simpler, okay? This is a very simple circuit. Two input pins, two gates, two output pins, and that's it. On the other hand, when you look at this circuit, it also is representing something that we have never seen before. Because with the adder circuit, okay, even as complex as K3 was, when you look at the flow of change, it's easy to analyze because everything starts from the input pin, then it goes through the first level of gates, then it goes through the second level of gate. A single OR gate is the second level, and then the output of the second level of gate is going to go to the output pin, and that's it, right? So it's very clear about the dependency of the calculation. This output pin depends on this OR gate. This OR gate depends on 3 different AND gates, and so on and so forth. So it's pretty easy to analyze, okay, if I change the input this way, the output is going to change that way. So that's pretty easy. When you look at this circuit, it is not that easy, right? Because you can see how the output of one NAND gate becomes the input of another NAND gate, but it goes exactly the same way back, okay? If you look at the output of N2, it goes back to one of the inputs of N1. So the analysis of this circuit is a little bit different now. But the notes specifies exactly how to analyze that, okay? So it starts with, let's just assume that S and R are both zeros, and we want to find out what the output is going to look like. So for that purpose, I am going to do this. Okay, so we cannot visually see what is going on. I know some of you can remember what you just saw, okay, but from the perspective of analysis, we just look at it this way. Okay, we just go like, okay, let's just say that we did not know, okay, anything about what the circuit as a whole does, okay, and we just want to do one analysis step by step. So what cannot change are the states of the input pins, okay? So these two cannot change because they are the input parameters to a quote-unquote subroutine, which is this particular circuit. So you can immediately see that one of these zeros goes into a NAND gate, and because it's a NAND gate, that means the output is guaranteed to be a 1 as long as one of the inputs, at least one of the inputs, is a 0. So we know Q is going to be a 1. But on the other hand, we look at R, which is a 0, and that cannot change, but it also goes into one of the inputs of another NAND gate. So you can also see that, oh, okay, so NQ is going to be a 1, because if at least one input of a NAND gate is a 0, the output of the NAND gate is guaranteed to be a 1. So from that analysis, we can now see that Q and NQ are both going to be 1s. when the input pins are 0 and 0 for both S and R. So when I enable the circuitry's simulation, we go like, okay, that's not too hard. Okay, we're good. So now the question is, what if we are to make a change to this circuit? Okay, what if we are to make a change in terms of the input pins? Let's just say that in the notes here we change R from a 0 to a 1. So we want to say, okay, what happens when I switch R from a 0 to a 1? Okay, well, let's not just click it, okay, because that would be way too simple, because the idea is we want to be able to understand how to figure this out ourselves. Okay, so if R switches from a 0 to a 1, S remains unchanged, then Q is going to be a 1 unchanged, because all it takes for N1 to output a 1 is at least one of its input pins being a 0, and S is continuing to be a 0, so that is not changed. So that means this 1 over here is going to continue to go to N2, one of the input pins of N2. So that part is guaranteed. So in other words, we analyze the circuit by starting with things that we already know has a known state. Okay, so now we look at the transition. This pin here, the first pin into N2, is guaranteed a 1. The second pin going into N2 is the one that is changing from a 0 to a 1. So now we'll be looking at two or both input pins of N2 both being 1s. But because this is a NAND gate, when both inputs are 1s, the output is a negated 1, which means it's going to be 0. So that means NQ is going to become 0 when I switch R from a 0 to a 1. Okay, so that is the analysis. Okay, and now that we know, what we are predicting the circuit to do, we can now do that in LogicSim just to verify what we have theorized a little bit earlier. Okay, so we click this. Okay, and sure enough, NQ turns into a 0. All right. So now we're going to analyze this circuit with another change. Okay, so the notes is already done here. Okay, this time we are switching S from a 0 to 1, maintaining R to be a 1. In other words, I'm just going to click here, and we want to see what's going to happen to this circuit. Okay, so we do exactly the same analysis. We start with things that are fixed already. We know R is a 1. Okay. And at this point, we know N2 is outputting a 0, just like that, right? So that is what we know at this point. Now we look at the transition. If S is to switch from a 0 to a 1, then the first input pin of N1 would go from 0 to a 1. However, that is not going to change anything, because the second input pin of N1 is still getting a 0 from N2. And as a result, the output of N1 will remain to be a 1. Okay? In other words, if I click this input pin at this point, Q and NQ will remain unchanged. The only thing that's going to change is this wire will go from dark green, which is a 0, to light green, which is a 1. The rest of the circuit will basically remain exactly the way it is now. So now we'll go ahead and give it a click like that, and we can see that, oh, okay, so the circuit remains unchanged. So do we have any questions about this circuit at this point? How we started off with both zeros as input pins. We first switch S to a 0. Nope, the other way. We first switch R to a 0, and then we switch S from a 0 to a 1. Then we switch S from a 0 to a 1. In that particular sequence. So do we have any questions about the behavior of the circuit by by the initial state 0 0 as the input, switching switching R from 0 to 1 first, then switching S from 0 to 1? Okay, we don't have any questions. All right, cool. All right, so now let's do it again. Okay, so let's reset both input pins to both zeros, just like last time. But this time we're going to transition the pins from 0 to 1 in the opposite order. Okay, So we'll first switch S from 0 to 1 first this time. Okay, so we'll switch this one first. So let's go ahead and try to figure out what's going to happen. R is going to remain unchanged. So R is a 0, which means N2 will continue to output a 1. So that output of 1 will continue to go to the second input of N1. But we are switching S from a 0 to 1. So N1 will now have both inputs being 1s, which means its output is going to be a 0, which means Q is going to be a 0. NQ remains to be a 1. Okay, so we switch that first. And okay, no big deal. Okay, just as predicted. So now we're going to switch R from 0 to 1. Okay, so we'll analyze the circuit the same way as last time. S is unchanged. It goes into N1, and N2 is outputting a 1 as well. So N1 has both inputs being 1s, and it's going to output a 0. That 0 still continues to go to the first input of N2. So N2 continues to have at least one of its inputs being a 0. So N2 will continue to output a 1 to NQ, whether I switch R to a 1 or not, because one of its inputs is already a 0. So R is kind of like, well, it doesn't matter at this point, because whether R is a 0 or 1, NQ will continue to be a 1. Okay, so we'll go ahead and do this, and we go like, okay, well, what is the big deal? Can anyone see what the big deal is? Okay, if you cannot see it, let me replicate the circuit so that we have two instances, but going through two different sequences of changes, state changes to the input pins. I think it will be much more obvious this time. Okay, so what I'll do is I'm going to reset both circuits. So they both start with 0 and 0 for S and R. Okay, so you can see how the outputs are the same. Okay, because we know that is going to be what the circuit would do. So with the first circuit, we first switch R from a 0 to a 1, and with the second circuit, we first switch S from a 0 to a 1, just like that. So you look at this, the states of the two circuits at this point, and this is hardly surprising, because if we know this is going to happen. So, but what is and they both have different input pins too, right? The input pins are in different states, so we kind of expect the output to be of different states as well. So, okay, we are not surprised. But what is interesting is, what if I switch this, S of the first circuit from a 0 to a 1, and I also do the switch from of R going from 0 to 1. Okay, so that we both have 1, 1 as inputs and 1, 1 as input to both of the circuits. Then you look at this and go like, whoa, hold on a second here. Why are the inputs the same, but the outputs are different? And Catherine is typing. I'm going to wait a little bit until I can see the question or the point. Yep, we got different we got quote unquote different results from the same input. So that is why this, what we call the SR latch, is interesting. It has to do with the feedback mechanism. It is a memory device. In other words, the circuit remembers what it was. Okay, I know it doesn't sound like memory the way we understand computer memory, but it is a very elemental memory device. It remembers its state. Yeah, I think Sakio got the right comment here. Whoa. Of course, I cannot imitate Keanu Reeves. Whoa. So are we having a really kind of big whoa moment here? I think so. Yeah, I think this is a pretty big moment. Okay, because we are looking at a memory. Yeah. Okay. Thank you, David. So this is our first most elemental memory device. Okay. So let's go back and review. Okay, how we set the memory and how it is retaining the state. Yep, so Catherine is also correct. Memory devices, has to do with the output being fed back into the input, okay? And therefore, it quote unquote reinforces, the memory, okay? So as it turns out, okay, if you want to change the state of a SR latch, okay, this is a SR latch and this is a second SR latch. So if you want to change the state of a SR latch, you just exercise one of these two pins, okay? S, by the way, is set. R is reset. Set means changing to 1, and reset means changing to a 0, which doesn't seem to make sense, right? Because if I want to reset Q, which is over here, I have to turn the R to a 0, okay, to reset. So just watch closely. Click it, it resets it, and then click it one more time, then it retains that state. If I want to change Q, to a 1, which means I'm trying to set the SR latch, I just have to change S to a 0 and change it back to a 1, and now it remembers that the new state is a 1. In other words, when both inputs are 1s, we're telling the SR latch and say, maintain your current state. If I change one of the two inputs to a 0, then it is performing whatever the pin is corresponding to. So if I change the S pin to a 0, it means we are setting. If I change the R pin to a 0, we are resetting. And if it's already set, if Q is already a 1, and you say, I want to set it again, nothing happens, no big deal, okay? But if it is already set and I want to reset it, it will go ahead and reset it, okay? So now here's a question, okay? The big question is, what if both of these, okay, are 0s and then they both switch to a 1 at exactly the same moment? In other words, we are telling the SR latch to both to set and reset at exactly the same time. What is it going to do? Isn't that kind of an interesting question? So I cannot do this manually, okay? Because I cannot click on these two pins fast enough that Logic will think that they're happening at exactly the same time. So what I'll do is I'm going to modify one of these circuits, get rid of one of the pins. Well, I don't need to get rid of the pin, I just need to change how everything is connected. So I can now connect the wiring of the second SR latch so that the R pin is completely ignored and the S pin is now connected to both the first pin of N1 and also the second pin of N2. So this time when I change S, I'll be changing both input pins at exactly the same time. Okay, so before we go any further, let's try to theorize what's going to happen here. Okay, changing to a 0 is not a problem, because if I change S to a 0 at this point with the second SR latch, then at least one input of both N1 and N2 is going to be a 0, which means both N1 and N2 will output 1s. That is not a problem, okay? I can click this and go like, okay, not a problem, because it is just doing exactly what the first circuit is doing. The problem is, if I switch S from 0 to 1 on the second or the lower SR latch, we're going to have a problem. We're going to have a problem because if I switch the moment that the 1, S being a 1, goes into both of the input pins, both the first input pin of N1 and also the second input pin of N2, then both N1 and N2 will see both of the inputs of each gate being 1s. So N1 and N2 will simultaneously switch their outputs to 0s, okay? Which normally would not be a problem, except that 0 goes over to the input of each other, which means the second input of N1 and the first input of N2 will now switch to 0, which is going to force the output of both NAND gates to become 1s again. Okay, so how is this going to resolve, right? So if I click it, Logic would actually report a condition So let's go ahead and take a look at the condition that Logisim is going to indicate. Let me move the window over a little bit so you guys can all see it. It says oscillation apparent. Okay, in other words, we have just created a quote-unquote clock where the frequency is kind of undetermined. Okay, so let me explain why it is happening. So I'll first switch this back to a 0, and it's not letting me do it because it is stuck at this point. So I'm going to reset the circuit and re-enable it. There we go. All right, so let me explain what is going on here. Now, I think most of you still remember what is a gate propagation, right? Because it takes time for the gate of a this time when I say the gate, I'm talking about the gate pin of a transistor. Okay, it takes time for the gate pin of a transistor to change its state. Now, there's no way around this problem because of physical characteristics. There's capacitance, there's inductance, and there's also resistance. So between those three, you simply cannot change the state of the gate of a transistor simultaneously. So it takes time. Okay, so when I switch the input pin as from a 0 to a 1, it takes time for N1 to change its output to become a 0. It would take about the same amount of time for N2 to change its output to be a 0. So all that time, okay, we have S being a 1, and then over time, both outputs would then become zeros. Now we know that those two zeros, one goes all the way back to the first input pin of N2, and the other one goes all the way back to the second input pin of N1. So there will be a very brief amount of time when both the output is a 0 out of N1 and N2. No, I take it back. Where this wire is a 0, this node is a 0, this node is also a 0. So there will be a very brief moment when they're all zeros, because it takes time for this change, for this node becoming a 0 it takes time before the N1 responds to it so that its output becomes a 1. And the same way over here, okay, when this node turns from a 1 to a 0, there's a short delay between the event that the node changes from a 0 to a 1 to N2 outputting, changing its output. So that particular propagational delay determines the half-life cycle of a complete cycle or wave coming out of these two gates. And it will basically just oscillate. Okay, so the frequency of the oscillation has to do with the propagational delay that is inherent to the NAND 2 gate over here, which is then inherent to the how fast you can switch a transistor that is underlying N1 and N2. But it will oscillate. All right. So are we okay at this point? Or are there any specific questions regarding the SR latch? All right. So the truth table of the SR latch looks kind of funny, because the way we look at it is if both input pins are zeros, then both output pins are going to be ones. If one input pin is a 0 but the other one is a 1, we also know what the output is going to be. But if both input pins are 1s, then we use some kind of strange description to describe Q and NQ. And that turns out to be no change. Okay, NC stands for no change. So in the state when both inputs are 1s, the device, the SR latch, is maintaining its state, which otherwise is known as a memory device. So the SR latch is our most basic memory circuit in the implementation of anything that can remember something in the computer. So are we okay at this point, or do we have any questions? right. So we got a question here. Oh, okay, it's not a question. That's from a while back. All right. So we can now continue to talk about a D flip-flop. Okay, so here's a D flip-flop here. So a D flip-flop is a little bit more complicated, and one thing we notice about the D flip-flop is it makes use of SR latch. Okay, it contains exactly one SR latch in it, but on top of the SR latch, it also has two NAND gates. So it has two NAND gates, one specific NOT gate, and this is how we make all the connections. So let's go ahead and take a look at a D flip-flop. So what we'll do is we are removing the second SR latch from this diagram and turning this into its own component, and then we have to remember to change its name to SR latch. Okay, like so. And now we can create the bigger circuit, which is a D flip-flop. So we go to project, we add a new circuit, and we call it DFF for D flip-flop. And we'll now pull the components in. Okay, so we have two input pins, but these input pins are labeled differently. One is D, which is data, and the other one is EN, which is enable. And then we got two output pins, Q and NQ, just like last time. So we got Q and NQ. All right, and then we got a whole bunch of other components. The first thing is we got two NAND gates. So we go to gates and we pull two input NAND gates. I could have just copied and pasted, but that's okay. And one is called N1. The other one is called N2. And then we got an SR latch. So we go to SR latch, pull one of those, and the SR latch is labeled SR. All right, so we got, I used an AND gate. Oh, okay, you're right. Okay, instead of a NAND gate. Okay, NAND gate. There we go. Thank you. N1, and here's N2. There we go. And we got a NOT gate because there's a single NOT gate here, which we'll call N. All right, so these are the components, and then what we'll do is we'll wire them up. So the way we wire up the components would be the nodes. So the nodes are dictating how we wire up the things. So we got D connected to the first input of N1. Okay, so we'll just line up things as much as possible. There we go. And we also want that to go to the input of the NOT gate. All right, so here's the NOT gate. And we'll connect that. So that we are now done with the first node. The second node connects EN to the second input pin of N1. Okay, so let's do that. There we go. And we also want to connect it to the first input pin of N2. So there we go. Oh, might as well line things up a little bit. There we go. So now we are done with the second node. The third node connects the output of the NOT gate to the second input of the NAND gate. All right. Well, we can make this look a little bit nicer. Okay, so we'll go ahead and rotate our NOT so that it is facing south. Get rid of this wire, which is not used. There we go. And now this connects to the second input of N2. So we are now done with the third node. The fourth node connects the output of N1 to the S pin of the SR latch. Okay, so there we go. And then the fifth node connects the output of N2 to the R of the SR latch, like so. And then the rest is pretty simple because we just have Q and NQ corresponding to Q and NQ of the SR latch. So this connects here. And yes, we do have a red wire because we never really quite say, what is the initial state of a SR latch, and they're both ones to begin with. In other words, we created this SR latch, and the initial condition is to say, hey, SR latch, just maintain whatever state you have. And then the SR latch is saying, but I just got created. Nobody told me what my initial state is supposed to be. Whatever, okay, just maintain that, right? And that's why the output of the SR latch are errors, because it doesn't really have an initial state. It is uninitialized. Okay, so what we'll do now is we'll take a look at this circuit and ask the question, what if I maintain D to be 0, but I change En from a 0 to a 1? Okay, so let's see what's going to happen here. So more importantly, okay, what the circuit is going to do is kind of important because that's kind of part of what the lecture is about. But more importantly, I want you guys to learn how to analyze a circuit like this, okay? So we say, okay, D is a 0, and as long as one of the inputs of a NAND gate is a 0, the output is going to be a 1, okay? That explains that. And En is also a 0 at this point, and as a result, N2 is also going to output a 1. Okay, so that's kind of explained. And the overall behavior of an SR latch is if both inputs, if both S and R are 1s, then it just maintains its current state. But the current state is undefined, and that's why we see the error bits as the output. So the whole circuit is explained at this point. So the question is, what if I change En from a 0 to a 1? Okay, so we'll analyze the circuit by looking at how the nodes are going to change. This node is going to change from a 0 to a 1. It will have 0 change to N1 because N1 has the first input coming from D, which is still going to be a 0. So N1 is still going to output a 1. However, N2 is going to change because the second input of N2 is a 1 because D is a 0. So if I change En from a 0 to a 1, N2 is going to output a 0 over here. And we already know that if we change R of an SR latch to be a 0, it is resetting the state of the SR latch, which means Q is going to be a 0 and NQ is going to be a 1. That is the prediction, okay, based on how we analyze the circuitry. So we'll go ahead and do it, okay, change En from a 0 to a 1, and sure enough, okay, we got rid of the error state because now we are specifically telling the SR latch to reset because the R pin becomes a 0, okay? So then the next question is, what if I turn off En at this point? In other words, we'll go back to the first state where both inputs are 0s. Once again, D is a 0 already, N1 only needs at least one of its input pin to be a 0 for the output to be a 1. So we know the output of N1 is going to maintain, it's still going to be a 1. However, with N2, it's a little bit different because if I switch En from a 1 to a 0, then N2 will once again have at least one of its inputs being a 0, which means its output is going to be a 1. So the SR latch will now see both the S and the R pins to be 1s. But that's okay, because we know that if both inputs to an SR latch are 1s, we're basically just telling the SR latch to maintain its current output state. So Q and NQ will remain the way they are. Okay, Q is going to be a 0 and NQ is going to be a 1 if I change En from a 1 to a 0. Aha, Okay, so that's good. So far so good, right? And then the next question is to ask, what if I change D at this point? I keep En a 0, but I change D from a 0 to a 1. What's going to happen? Well, that's an easy one to analyze because we can see how this particular node, how En is connected to both N2 and N1. So as long as En, or the enable, is a 0, N1 and N2 will continue to output 1s regardless of what D is. Okay, so that means as long as En is a 0, we are telling the SR latch to maintain its current state. Okay, which is kind of cool because now we can flip D all day long, okay, and nothing happens, okay, because En is a 0. And that's why En is called an enable pin, because if the enable pin is a 0, we are not enabling the SR latch to change its state. Okay, the En pin has to be a 1 in order for the SR latch to change its state. So let's go ahead and enable the turn enable into a 1 again, and this time we'll see what happens that when we click on the D pin. So we have En being a 1, so the device is enabled, but we are changing the data bit, the input, from a 0 to a 1. Let's check out what's going to happen here. So En being a 1 means that N2, both N1 and N2 will have one of their input pins being a 1 because those are coming from the enable pin. But if I switch D from a 0 to a 1, okay, the first thing that's going to happen is N1 will now have both of its input pins being 1s, which means the output pin of N1 is going to be a 0. It is telling the SR latch to set its output. But we also want to see what's going to happen to N2. If D is a 1, then the negation of that is going to be a 0. So N2 will now become a 1, so the R pin of the SR latch is going to be a 1. In other words, if I were to click this input pin here, then the S pin of the SR latch is going to be a 0, telling the SR latch to set its output, but the R pin of the SR latch is going to be a 1, which is not doing a single thing. It's not asking the SR latch to reset. So we are only asking the SR latch to set, just like that. Okay. S and R cannot, yes, they are flipped at exactly the same time, but they are of different states. Well, more or less the same time. They're not exactly the same, Richard, because one has to go through a NOT gate. So the output, or N2, is actually changing its output with just a little bit delay compared to N1. Because the NOT gate. So how can it reset to 0 first? Oh, you just have to turn D to a 0. Because that's the data to be remembered, and the enable says, should I remember? Okay? So this is called a D flip-flop. So D flip-flop is resembling what we know as memory in a computer a little bit better compared to an SR latch, because D is specifying what we want a D flip-flop to remember, and then En is telling the D flip-flop whether it should remember or not. So if En is a 0, we're telling the D flip-flop to ignore the D input and just say, don't remember a single thing that you see on the D pin because you are not enabled. But as long as enable En is a 1, we are telling the D flip-flop to mirror its output to the D pin. Okay, so as long as the En pin is a 1, we are enabling the device to change its state. Okay, which is kind of cool, but at the same time, this is not sufficient for what we need to do inside a processor. We are running out of time today. It's 10:22 right now. So in terms of the lecture, we are running out of time. But I do want all of you to spend some time to at least read through this entire module. Okay, because by the time we are done with this entire module, by the time we get to the multi-bit registers, that becomes the most basic component inside a processor. Okay, so we are just building up to one of the simplest components inside a processor, but it is a very, very important component nonetheless. So that's what we'll do tomorrow, is to finish the rest of this module, and then we'll start to look into the other components, components other than the register inside a processor. And by the time we get to this point, the ordering of the topics, I can deviate a little bit because I'm still trying to find out what is the best way to introduce those topics. But at this point, okay, for today, we still want to kind of continue with the understanding of what a register is inside the processor. And your current lab, I believe, has no passcode to it, but let me just double check to make sure. So we are scrolling back to positive exponent, which means the exponent of 10 starts with a positive value, and the job of your code is to turn it into a 0 eventually. The time frame, I only give you like 2 days to work on this one, mostly because if you have already worked on your negative exponent, the positive exponent is exactly the opposite. We are trying to multiply the mantissa by 10, and we're trying to use division by 2 to make room, as opposed to the other one is trying to increment the exponent of 10 by decrementing the exponent of 2. So they are basically quote-unquote flip side of each other. The way you do this, you can use the same file. Okay, if you're using a monolithic file to work on the negative exponent, you can continue to use the same file because the logic of these two loops should not interfere, because one stays in the loop as long as EXP10 is negative, the other one stays in the loop, its own loop, when the exponent of 10 is positive. So they should not interfere with each other at all. Okay, and Catherine is typing something. Yeah. I can give you one of the test values is the one that I just worked on in the spreadsheet. So if you, oh, you know what? I can do better than that. Positive exponent questions. And I think the description itself, the question itself, gives you an example. This is the one. So use 1.2345678 E30, and this is a partial output of how the mantissa EXP10 and EXP2 should change over time. So this is actually a very good example because it shows you at least the first. No, it shows you all the steps. Actually, this one shows you all the steps. Your initial mantissa as an unsigned 64-bit integer is going to look like this, and eventually it will become this. So does that answer the question? Alright, so are we still using 64 bits? Yes. So in the example in the spreadsheet, I was only using 16-bit because otherwise it will. Okay, there are two reasons why I did that. Okay, the reason why I use a 16-bit mantissa is so that I can show a few cycles really quickly. Because if I were to use 64 bits, you can see that it would take a long time before I run out of digits. But the most important part is in the spreadsheet, and that applies to Calc, it applies to Google Spreadsheet, and it also applies to Excel, is internally it does not know what is a 64-bit unsigned integer, and internally everything is a double in a spreadsheet. So that means I can't really keep track of exact values past a certain point. So that's the second reason why I kind of shrunk the width of the integer down to 16 bits. And Robert is typing something. Yes, so you're getting an extra day to complete the labs. You got 2 days to complete the second lab. The first lab you kind of got a bunch more time because it's over the weekend and it started on what, the Thursday or the Wednesday. So you got a lot of time for the first lab, but the second lab, once you got the first lab done, the second lab is actually a whole lot easier. Yep. So Robert, you're correct. It is due on the 1st of July. All right. So if there are no additional questions, I am going to stop the live stream, and then I'll take a 10-minute break and be back at 10, let's call it 39. All right.